So this is your exam week, and your holy vacation starts from here, 18th.
13 to 18.
Yeah, that's what. So today, when is Holi, by the way? When is Holi?
It's on
18.
18th, ma'am.
So holy vacation, you have no teaching, right? It is a vacation for the student, not for us. 13th to 18th, right?
Yes, ma'am. Tentatively till 20th.
Me too, up to here. Yeah, so Saturday, Sunday, of course.
Yes, ma'am.
And when is Holi, by the way?
It's on 18th, ma'am. Holi
18th.
is on 18th.
Oh, 18th. That's and this whole. So after your exam, you have 1 week break. Studying, I mean, no lectures. And
Yes, ma'am.
Yes, ma'am.
Mid-sem break.
so now, how about so now 7 to 12? All the days you have exam. When is it that you don't have exam? Because I
We
have
have exam from 9 to 12. From 9th to 12th. But we have one more examination, and for that, the date has not been given yet.
okay. So I will confirm before that exam. So if you have to tell them, you just keep our slot in mind. So now you tell me what is your comfort level. I'll take in that week only 7 to 12. So how about 7th Monday during your, so let's say Monday when I have my class, it ends at 11:30. So from 11:30 you have another, so that is your exam week. So you will not have any other thing, right? Any lecture, right? On 7th, let's say.
मैम
अगर
एग्जाम
एग्जाम
इज
में
ऑन
है तो कोई लेक्चर नहीं होगा ना.
But no, ma'am, we will be having lectures. The exam will be starting from 9th.
यस
Yeah, 9th, but you will have lectures on 7th and 8th also, let's say.
यस
Yes, ma'am, we are having lectures. Nothing is announced about that if we are not having lectures.
Pardon?
मैम इट इज नॉट एक्चुअली announced but by experience of previous 3 semester we were having class before exam
Okay, then how about when can I take your exam? You tell me, because your comfort level we will plan. So
मैम
how about,
exam is on Moodle or Metal
no, okay, let me tell you, I have said before also, it will be an open book exam.
okay.
And no Moodle I cannot take, because if you write one equation, it will take so much of time, hardly what you will do in the paper. So you will have A4 size paper or a full scape. A4 size is preferable, blank pages with a good pen. You will write down in a legible way. And then using cam scanner of your phone, you will scan and upload it. In detail, we will tell you the information, how the things will work, either on Google form or whatever. But the truth is that you will have an open book exam where you will give it the way you do it here in the way you give the exam normal, pen and paper, but you can use anything, your internet, your friends help. Okay, it's an open book exam.
Ma'am,
So
how much time we will get means
yeah. So
exam
now see, now with so much of leniency in the exam that making it an open book, I cannot give too much of time. So 50 marks, 50, and 1.5 hour. In that 1.5 hour, you will have to scan and upload and everything by time. If it is late, we cannot consider your answer sheets. So in 1.5 hour and in 50 minutes, 50 marks paper, and 1.5 hour in all, you will finish it and upload and everything. And you can help your friends, but my advice is that this is a relative grading and they are all competing with you. Okay, so you can be nice, the whole life is there, but I mean, open book means it's not that I am telling you that you copy. Okay, this is not that way. Copying is forbidden. It's not at all allowed. It is illegal. Open book is just limited to yourself. You use anything. You can use your textbook or whatever. So after that, if there is if you up to 2 decimals, you write down your answers. If it is wrong, we will cut the marks. If the units are wrong, also we will cut the marks. And also keep in mind that when we set the paper, we will of course keep in mind that you will not find answers by just looking to, and the time is 1.5 hours in all everything you have to do, right? Because what happens is, let's say if somebody is excellent, okay, and doing everything, or dekhna pade to thoda that is okay, but is otherwise good, and one has not worked at all, right? So then if you are searching also, you will miss two problems, okay? So time is very crucial. So I'm explaining you the logic also why it is crucial. It is to filter out and differentiate a good student and the one who has not worked so well. Okay, so that's what. Anything else if you want to ask me, tell me. And what is the date that we will fix that? We will do it now. But finally, I will leave a message after talking to the class B of yours. Meaning, after talking to the professor, Nalin, we will finalize and come back. But I need your input so that we finalize accordingly.
Ma'am, like if possible, the exam could be on 7th or 8th, and like you could confirm if we have no lectures, because other batches already have exams at that time. So if
That's what I'm telling you, that that is an exam week. So I don't think so you will have lectures. But let's say you have, even if you have lectures, see right now also how many have been here for the lecture. Right? Anyway, so okay, I hope that you remain present in that other lecture also. But on Monday, let's say, after my lecture, you have another lecture on Monday. What's to us, let's say. Sorry,
yes,
Tuesday I
ma'am.
have no, sorry, Tuesday I have a lecture. Okay. That is
Yes,
10:15.
ma'am. Tuesday we have lectures till 1:15, and then we have lab in the afternoon time.
Okay. So your next lecture after my starts at what time?
12, ma'am.
12 o'clock. So if I keep time from, and then before my lecture, what do you have?
We have a lecture from 8:30 to 9:45.
8:30 to 9:30. Hai na?
Yeah.
So I can keep 10 to 11:30. Was to worst if somebody wishes to attend or late hai. Otherwise, it's an exam week, as I say. So on my lecture time, that is on 8th. Okay. If you don't have any other exam provided, then it will be from 10 o'clock to 11:30. Is that okay on 8th Tuesday?
Okay.
Okay, 10 o'clock to 11:30. So that, and that is common to the whole class. Same thing will be with part B. So after having a word with Professor Nalin, we will fix for 8 during your lecture time. Just will start 15 minutes early. If you want to attend previous lecture, you can, else not, because this is an exam week. Otherwise, also, if I would have done by metal, they have to give me a slot, right? So you think that this is given after I have talked with you, we will finalize as 8 for now. For now, no, this is final. And Nalin will also do accordingly. But officially, I will tell you once I have a word with him. Okay? Because
Yes, ma'am.
we cannot go on lingering or take some odd time. Okay, you guys are at home, but this is a vacation and students, they plan or whosoever, right? They have some plans, tickets. So I have to finish it in this week. I cannot take early, nor can I take later on. Okay, so with that note, we will go here. And yeah, and our syllabus will be, again, I have to ensure that and we may be a little bit aage piche, myself and Professor Nalin, but whatever I teach, let's say up to 4th Friday, in 4th nahi rakhte, up to 1st, okay, will be your syllabus. So lecture on 1st up to will be your syllabus, and that also finally I will tell you. So see, we were with this device BJT, and as you know that it is a physical device. It has a making. It is made up of some material. That material is semiconductor. I am just briefing you, okay, the sequence of the highlights of this. And it is made up of back-to-back connected junction diodes, right? And it has 3 terminals. And based on how you connect your supply, your battery, right, you have 4 different regions of operation. Okay, and our goal, the course being on analog circuit, our goal is to, extensively study analog circuit, in which amplifier is one of the main component, is one of the main circuit. In addition to that, we will see few others also by time. But for now, and when you talk of an amplifier, it has to be biased. If you bias this in forward and reverse region, it will work as an amplifier. And the other regions, as you can see, we have covered it, known as cutoff saturation, is to make it work in a digital domain for on and off. Okay, so as a switch. But here you are amplifying, meaning that for little input that you are giving, you will get output that is amplified. Okay, so what does it mean? That if it is a black box and you are giving, it can, so now that amplifier can be, different kinds of amplifier. It can be a voltage amplifier, it can be a current amplifier, where we are getting voltage in multiple terms. Okay, and then current amplifier, so where current is amplified, and then transconductance, impedance. We will see all this once we move ahead. But for now, when I say an amplifier, you can think of voltage in terms of voltage. Okay, so input voltage you are giving, and you are getting a higher output voltage, which is 20, 50 times more, 100 times more. Okay, so now you must understand another thing also, that this voltages are developed because of the current. Okay, so to get more amplification, you need more current. Okay, and how to get more current and all we will see. So this voltage is developed because of the current that is flowing. And when a current is flowing through a load, a resistive load, and when a current is flowing through R, then the potential is developed, right? So that V is equal to IR, like that. So that's the goal. And this connections we have extensively done. I have explained you, this is for an active mode, where this is for an NPN transistor. Okay, and I explained you the significance of PNP also. And this, as far as amplifiers are concerned, you can construct an amplifier using NPN and PNP. Thing is that you have to bias it in an active mode. Here is a bias that is shown for an active mode, where this junction, that is emitter base junction, is forward biased. Okay, so it works like a diode, whereas the collector base junction is reverse biased. And the goal of this is that the electrons that diffuse into the base, okay, they are sucked, they are collected at this terminal. That's why the reverse bias significance is in terms of attracting the electrons towards this terminal and giving a potential that is positive to attract the electrons that are collected here, and hence create a current. So that's the reason why we reverse biased it. And we have seen that as long as it is reverse biased, irrespective of the voltage, right, it will work in the active mode, where IC is proportional to IE, and IE depends on this voltage VBE. Higher the VBE, higher the IE, and hence higher IC. Therefore, or hence, you can say that IC depends on VBE and not on VCB as far as it is reverse biased. Okay, so I'm just briefing what we did. And this were equations for finding, so in terms of the cross-section area, the diffusivity of the electrons, the doping, right? And the concentration of the charges, you get the current. So current is a product of this, as we had seen. And that IC is equal to IN. So, and that IC, IN, we found out. So in terms of scale current, IC is equal to IS, where IS is equal to this. Okay, that's what we had found out. So if you go back and see. And then, right, so this is, so these are the parameters where Ni and Na are the intrinsic. Intrinsic means in a pure form, what is the carrier density and the doping concentration of the base. So if the base is doped heavily, okay, then IS will decrease. So we need a lightly doped, because if it is doped heavily, there are a lot of holes in the base, then recombination will happen and you will get less electrons to create current. More electrons, more current. Less electron, less current, right? So if the recombination happens of the most of the electron, because if the holes are more, then it will recombine. If less holes are there, then less recombination and hence more electrons. So things like that. As you can understand, it's very logical. And these are the physics-based equations that have been derived since more than half a century. So we don't have to derive, we accept it. And here IS is the scale current. Okay, and what is the magnitude of that? It's less than pico ampere even. Okay, so that is referred as scale current. The other thing now we did up to here. Okay, so anybody, any doubt? Then I can start with my today's lecture. I just briefed you in case you have forgotten. Okay, so how many currents you have? Who will tell me fast in all? How many currents you have and how many voltages you have?
Ma'am, we are having 3 currents and 3 voltages.
3 voltage, happy.
Sorry, I said 2 voltages and 3 currents.
Yeah, very good. So in all you have 3 currents. So now see, as an engineer, again I am telling the same thing. Your goal will be that, okay, you are given a specification. For example, that you will be given a pressure sensor or a ECG, okay, which will measure. So ECG you can understand that it will measure your heart beats, right? It will give a waveform. ECG if you have seen, and there will be peaks and like that way. So you can know from that, and if it's a straight line, one is dead. But these ECG signals, they are very weak. And then if you want to process that, you have to amplify that. Okay. So you will know that, okay, my output of the sensor will be this much and I need to amplify this much. Okay. So as an engineer, you have to design how much voltage to give, what kind of BJT to use, right? And then all this, what are the, because when you make a circuit, it's not only just BJT, you have to give the correct voltage and hence the biasing. So there will be resistors also. Then other things will come later on. We will see frequency also matters, right? Because you know what is frequency, right? If an AC signal, for example, has different frequencies from 1 hertz to terahertz and higher than that. Now, any device, right? It will not work for all range of frequencies. It is only capable to work for some range of frequencies. And where does that come from? Okay, so this is all physics that you will. It's all very easy once I explain you. But then the frequency also comes. So as an engineer, you have to understand that your input frequency is this much, your input voltage is this much, your current is this much, and you want this much of gain. So you have to design. Now the design, if somebody gives you a BJT and just from this design needs parameters, okay, and analysis, because there are a set of equations you will analyze and do all those paperwork. And for that, we have to define some parameters and the relationship between this. That how, if you have now 3 currents, I, IC, IB, right? How are they related? So if you and then so based on that, we will have some new parameters. Okay, but they are basic parameters are these 3. From that, we will generate some new parameters to make our design and analysis efficient, or to define some parameters of your device. So these are the basics one, and this is also the voltage that are needed are the basic parameters. Now, if you relate IE with IB, okay, then what is that parameter? If you relate IC with IB, IC with IE, what is that parameter? So let us see that. Okay, so that's what we are going to see now. And let's say the first parameter. We did this now or no? Here, I am here. Sorry. So we are with the base current now. Collector current, we did all this. Now we are with the base current, okay? We are with this slide, I did up to this last one. so we talked no last time that this IC, the scale current IC is given by this equation and it is dependent on VBE. It's dependent on this VBE. Okay, and here it is IIS is the scale current, which is given by this parameters, which is defined for a particular VJT. Okay, with doping concentration, cross section area. This is given in the data sheet. So then this IS is of the order of it is less than pico ampere. Okay, so that's what we did last time. And now the base current. Now what is the base current? As you know that in the base, this is for an NPN. Okay, NPN transistor. So there are two components of the base current, IB1 and IB2, where IB1 is due to the holes injected from base region into the emitter, right? So the electrons are moving from the emitter to the base, and at the same time the holes are moving from the base to the emitter, but holes are very few. So as I explained you last time, that if there are 100 electrons in the emitter and let's say two to three holes only, okay, then one or okay, let's say 4 holes, okay, then 2 will recombine with the electron and 2 will move towards, because of the diffusion, towards the emitter, okay, and 96 of the electrons will make it to the collector, so something like that. So that is what IB, and then IB. So now the recombination has happened, and the holes that was there, the holes that were available in the base region, right, they are exhausted. So you will need more holes to be created. So IB2 is the holes due to holes that have to be supplied by the external circuit, okay, to replace, because they have recombined. We will need more holes which will be given by the supply. So this too will make the base current IB. And how it is related to IC? It is related by a parameter. This parameter, very important. Okay, this is like a king of your studies. So this is beta. And beta is, if you bring beta this side, it is a ratio. It is very simple. It is a ratio of IC upon IB. And IC is almost equal to IE, but it is not equal to IE, as you can understand. If IE is 100 electron, IC is 96. Okay, so beta is an important parameter which relates IC with IB, and it's a ratio of IC to IB. And that is beta. So this is a transistor parameter, and once we go ahead, you will understand how important it is. So if any one of the current is given and beta is given, then you can find out the other one. Okay, and you can also give this as IB in terms of IC. You have this equation for IC, so you can replace this here and beta. So this just derived from this, very simple. Okay, and beta. We say beta, but the name of the parameter, okay, so this is the symbol beta. The parameter is known as common emitter current gain, and the significance of that you will soon understand. Now, this is common emitter current gain. So this is the configuration. So you have 3 terminals: emitter, base, and collector. And how you connect, because you are giving an input, you are taking an output. Okay, so now if you are giving an input and there are 3 terminals, emitter, base, collector. If there are 3 terminals and you are giving an input to, now let's say that this is your, this black box is your transistor, and this is going to make an amplifier. We have to give supply, we will add some more components, whatever is needed to this transistor. But let's say that you have these 3 terminals, 1, 2, and 3. Okay, so where you will give the input, where you will take the output. So it depends on how you connect. Okay, so to get an amplifier, so now you know so what is the best connection that you can do, where you will, so out of these 3 you will give input across 2 terminal, because input you cannot give input across 3 terminal. Across any of these 2 terminal you will give an input. So any of the 2 terminal you will get an output, right? But which and how, so that is very important. And for that, we will see that this is one of the configuration that you will soon learn. So this is common emitter current gain. Okay, so when you connect this BJT in a common emitter configuration, you get a current gain. And that current gain is beta, which is defined by IC upon IB. And you must understand that if IB is 4 and IC is 100, then you can understand beta is really a big value. It is of the order of 50, 100, okay, 200. So you can understand the ratio of this. IB is very, very small, IC is really big, and beta is also a big number of the order of 50, 100, 200, like that. So, and then what does it depend on? Beta, because it's a ratio of the current, it will depend on the width of the base region. More the width, less the beta, okay? And because beta is proportional to IC and inversely proportional to IB, okay? And relative doping of the base emitter region. So it depends on the doping of this base emitter, heavily doped, right? Then you will have, and then doping of the base emitter region. If base is heavily doped, then what will happen? More recombination will happen and your IC will get less. So base is doped lighter compared to emitter which is doped heavier, because the current is because of the electron. But this is a bipolar device, meaning that the current is a function of both hole and electrons, but your current is made up of in NPN of the electrons. And high value of beta, how to get? So you will need a thin base. If it is a thicker base, then they will recombine and very less will make it to the IC. So, and then lightly doped base or heavily doped emitter, same thing. So now you must have all this clear picture in your mind. So up till here, is that correct? Is that clear to you? So in a simple way, beta is nothing but IC upon IB, ratio of that, and it is known as common emitter current gain. The significance of this terminology you will understand in the future lectures. Okay, so don't worry for now, but in brief, I just explained you it is the configuration that you get the maximum gain. An amplifier has a gain, and in which configuration you get the maximum gain, how you will give your input, how you will take your output, it depends on the configuration. Since there are 3 terminals, there are 3 configuration, and this is one of the configuration which is known as common emitter. The other 2 configurations are common base and common collector. Okay, but common emitter gives the best gain, and that's why when you want to make an amplifier, we will use common emitter configuration. Okay, and the gain that you get, that is IC upon IB, is your beta. So beta is when this is in common emitter configuration, that we will see in our future lectures later on. Okay, हाँ के ना समझानू मतलब? My connection is lost or what? You guys there?
Yes, ma'am, we are audible.
Yes, ma'am.
Okay, I am clear to you. Do you understand?
Yes.
Yes, ma'am.
Okay. So now there is another parameter like beta. There is another parameter alpha, and alpha is nothing but beta was what IC upon IB. Alpha is IC upon IE, and you must understand that alpha is what? See this. So alpha is IC upon IE. Okay, IC upon IE. Right? And who will tell me IC is more or IE is more?
IE is more.
IE.
Very good.
E.
IE is more because, as I said, if there are 100 electrons, that makes IE, 96 will make IC. So alpha is always less than
1.
1. And it is around 0.99 to around 0.99, 0.98. Okay, very good. Now, you have this alpha relation, you have beta relation, and you know this. Right? Then you can find out how alpha and beta are related. So alpha is equal to beta upon beta plus 1. So if either of them is given, you can find out the other one. So if let's say one current is given and beta is given, then you can find out IB. Okay, and then so if let's say to you IC is given and beta is given, then you can find out IB. If you can find out IB, then you have IC and IB now. You can find out I. Okay, if beta is given, then you can directly find out alpha also. So I mean, if any two parameters are given, you can find out others given provided this relationship is given to you. Okay, and this alpha, okay, this is the symbol alpha, but it is known as common base current gain. So here it was common emitter current gain. This is known as common base current gain. So it is, you think that this is like a name, Ram, Sham, okay, for now. The significance will become clear as I just briefed you, but maybe still you are wondering, but it will become clear in my next lectures. So now what happens? See, now the next thing, as I said, the final goal is to analyze. When you put this BJT and you want this gain, that gain, when you are making a circuit, let's say, right? So let's say this is your circuit, or you want to make a circuit for the application, kind of the application that I just described you, right? So you have to, but what you will have is, this is the input, I want this output, so I need this much gain, this is the BJT, so all those things. Now, to do that, you have to analyze the circuit. If you put this symbol here, you will not be able to analyze. Analyzing means using network theorems, network equations. You should be able to find out I and V. We should be able to quantify, okay, that I and V. That analysis has to be done. In order to do that analysis, this symbol will not speak anything. So what is the equivalent of this? So when you want to analyze, we have to find out the equivalent. Equations we have, but in terms of the equivalency of this, so there is a model of this, and we replace this BJT, because BJT is a symbol, but to analyze you need in terms of what? You need current source or voltage source, you need R. Okay, so this is the next thing that we are going to see is the model, and we will, when you want to analyze, you replace, like the diode model we had, right? So diode model will help you to analyze the diode circuit. The symbol just will not help you. So to analyze the circuit. So now, presence first order BJT model assumes. So we are assuming now. So we will see the model, and this model is for NPN transistor that I'm just going to show you, and that too in active mode. Okay. So in active mode means that emitter based junction is forward biased and the collector based junction is reverse biased. So that is your active mode where the BJT is used as an amplifier. So the basic relationship is collector current IC is related exponentially. So this is the main thing. And last time I explained you that this VB will be your input when you build the circuit. So this is at the base emitter, you will give an input and you will develop a IC collector current which is proportional to this input. Okay, so because when you want an amplification, your input and output have to be proportional. Your output is proportional to the input, then you multiply that many times. It's 10 times, 20 times, it is more, but it is proportional. So here for the input voltage that you give, you get an IC which will develop a voltage at the load, which is proportional, because if IC is proportional, then and then, so if you are developing a voltage across a load R, let's say your resistor, R is a load resistor, which is an input impedance, you can say, of the next stage, then it is IC into R is the voltage. Okay, R is constant. Okay, R will not change. So your output voltage that is developed because of the input voltage VB is proportional to your input voltage VBE, because output is proportional to IC and IC is proportional to VBE. Okay, so we will see all those things in detail, but just and then it remains independent of VCB as long as it is reverse biased. But yeah, there is a little dependency, as I was asked a question last time, and that also we will see, but that is not much, a little difference that we will soon see. Now see, this is the model. So model, as I said, when you want to analyze or you want to derive, right, you will use this model, and this is the model of an NPN transistor which is in an active mode. So here it is CBE. Okay, so these are the three terminals that you will first draw. Okay, and so these are your three terminals here, and now see your B and E. Okay, so because of the emitter base junction, which is forward biased, okay, so that is your voltage VBE. So this is a forward bias diode. This is for an NPN. Okay, so with this kind of connection, right? So this is NPN, N. This is N. This is N. This is P. So this is forward biased. Okay, this is for an active mode. This model is because active is the mode where the BJT will be used as an amplifier. So when you want to design an amplifier, we will use this model which represents active mode. For other modes, I will soon show you. So here, for the active mode, this connection is just a forward bias diode. And here is the current IC. Here is IB and this is IE. So these are two input currents. This is output current. IE is equal to IC plus IB, as you can see. And this is the current source, which is given by this. IC is given by, as we have seen, this equation. And you can see that it is proportional to VBE. Where is this VBE? VBE is across this base emitter. So that is across here. And this is a constant current source. But this current, it depends on this voltage VBE, which we will see that is making an input to your circuit later on, okay, when we build the circuit. So this is VBE. So this is a current source. This is a current source which is dependent on this VBE. So this is a voltage dependent current source, you can say. And why current source? Because it is giving IC, which is almost constant, irrespective of VBE. We will soon see the graph also. Okay, so the current is IC, which will be developed at the load. It will go to the output. Okay, so IC is the current, and then you have two voltage sources. So you will have two graphs that we will soon see. And then here, as you know, that this is IS. This is for an emitter here. So that is IS upon alpha. That is the relation. This is IE. Okay. So IE is nothing but IC upon alpha. So this ISE is given by IS upon alpha. This is for emitter. So the point here to make is. And the other model that you can give is IC is also equal to alpha IE. Okay, so both of them are current. Both of them are correct. Okay, here it is dependent on the voltage IC. Here IC depends on IE. So what happens is when you are analyzing, sometimes you will have either IE or the voltage, either of them. You may have IE. Then you use this model. If you have in terms of voltage, then you will use this model. Okay. So given the input conditions, you will use either of the model. Both are same. So here this is known as voltage dependent current source. This is current dependent current source. IE is the current and IC is the also current. So it is current dependent current source. Okay. And then what is this alpha? Yeah, so here you have if you remember in the beginning, we have 4 regions, and what we are talking here is you have active region and you have reverse active also. And we are talking of this active region. Okay, what is reverse active? We will see that. We are talking of this active. In the reverse active, EB is reverse biased and CB is forward biased. And then if you see this as a BJT, this is symmetrical device. Okay, here symmetry means that these both are of the same size dimensions, emitter collector, and in between is the base. So symmetrical device means if it is a symmetrical device, if it was fabricated this way, Then depending on the voltage, right, your emitter, and this terminal can be your emitter also, this terminal can be your collector also, depending on how you give the voltage. So if this is a symmetrical device and if you forward bias this and reverse bias this is your emitter. But if you forward bias this and reverse bias this, then this will be your emitter. If it's a symmetrical device, but as I said, it's not a symmetrical device, and it looks like this. Now, why this? Why it is made like this way? That I will soon explain you. So you have in short two models, and yeah, so this is voltage dependent current source and this is current dependent current source. So current controlled current source. Okay, so this is current, I is the current controlled current source, and this is voltage controlled. This is the voltage that is controlling. So depending on the conditions that is given to you, you have this model, both are same. If you're in a problem, you are given in terms of IE, you will use this model. If VB is given, you will use this model.
Are these two models up for the same transistor?
Yeah. This is of the same transistor in when you want to analyze for an amplifier in the active mode. Okay. For the active mode, this is either of the model you get. So wherever there is a BJT, right? You know, in the BJT, where is, so I'll talk of the symbol and everything. So be patient. And wherever the BJT, you know that there is EBC, you will remove the BJT and fix this. Okay. And then we will do the analysis. Slowly, things will become clear.
Okay.
So now, as I said, now this figure, it is showing a more realistic. This is how in the cross section, if you take, it will look like this. Now, this is E emitter, this is base, and this is collector. Okay, so this is surrounding, the base is surrounding the emitter and the collector is surrounding this both of them. Now, what is the significance of this? Now, see, what happens is that when the electrons are generated and they are running inside, and they get collected at the collector. So it is like sucked heavily. So they are all accelerating. They are all running fast. I cannot say moving, but running is a better word. And when it happens, it will heat up the device. Okay. And heating of the device will alter the characteristic curve. So if the same device gets heated up, it will not give the same current. The current quantity will change. Okay, the quantified value of the current, because for any device, if for the same temperature as a room temperature, it is okay. And then if it gets more heated further, then it will get destroyed. So heating will cause, change in the current and the IV characteristics in the nature, and then ultimately it may get destroyed. So that now, as you can understand, collector is collecting. So many electrons come with speed, and it is heat dissipation is happening, so that it happens efficiently, and it collects all the electrons. Nothing should be, going here and there. It should collect all of them. This is the way it is designed. Okay, so whatever is emitted will go through this thin base and will all get collected here. Since they are huge in number, large area or volume will facilitate heat dissipation. If this was a small area, right, because this is generating and passing here, so they are all, because it's like too many people, you need a bigger hole now. Otherwise, what will happen if you want to collect 50,000 or 1 lakh? You will need a bigger hole. If just 10 people, then small room is enough, like that. So similarly here also, to collect, because they all come, lot of heat is there that has to be dissipated. So a larger volume or an area of a collector is preferred. So that's why so when you forward bias this and then you reverse bias this junction, right, it will work in an active mode. But if you do the other way, right, then from here they will be generated and get collected here. Now, that's not an efficient way. Again, this guy will get heated up so much, because now this literally, so to make the device more efficient, this is the way it is fabricated. Okay, so collector virtually surrounds the entire emitter region, right? And this makes it difficult for electrons injected into base to escape collector. So whatever is injected has to come here only. It cannot escape from anywhere. and device is not symmetrical. Understand? Initially, it was just to make a point to you. As such, emitter and collector cannot be interchanged. Okay, so what if it was symmetrical? The way I showed you in the beginning slide, and I just explained you, the way you give the voltage will define your emitter and collector, if that was the case. But the cross section is like this, the device is, because the way it is, yeah, living room is living room and bedroom is bedroom. Why, if you have a living room and a bedroom which is well planned, why do you want to exchange living room and a bedroom, right? Something like that. This is so this is a well planned device. It works efficiently if you connect this way, right? And connecting the other way will not make sense, because that will result in, less current and device getting heated up and maybe destroyed eventually. So that is what is about this reverse. This. Maybe it's not used. We are intelligent people, right? We will not use it if it is not efficient or of making not sense. So are you clear with this too? This I'll explain you later on by time. This too तो समझ में आया ना अभी थोड़ा?
Yes, ma'am.
Now, if you operate in a reverse active way, okay, this is the model. So if you, the reverse active way, if you see, this is for NPN, okay, NPN, where this is forward biased, right? Right, reverse active. So this EB is reverse bias, this is forward bias. That's what I think. So this is reverse active, which we don't use it, but by mistake, if somebody uses, okay, but it's not that efficient. And this is how this will be forward biased, okay, and you will have the current flowing. So yes, so this is the direction of the current that will flow if it is in reverse active mode. Okay, and this is alpha R, this is alpha F. In this case, it was alpha F, you can say, to differentiate. This is alpha F to differentiate, and this is alpha R for the reverse, because anyway, alpha and beta are the same thing. These three currents are all there. Alpha and beta is same. So alpha R IC. Now, what is alpha? Alpha is IE upon IC. IC will get cancelled. So IE. So this is IE current, which is given by alpha R IC. And alpha R is to just show the alpha for the reverse active mode, because that alpha and in the just the active forward active. So when you say reverse active, we will, for the active mode, we will say forward active. Forward active is the one that we use it, as you can understand now from how it is made. And the reverse active and forward active. So alpha by this subscript F and R to represent reverse and forward active. So here this is for the reverse active mode, this model is, okay. And this is IE, which is given by alpha IC, but since it is reverse active, this subscript R is there, okay. And here what is happening, this is collector base junction is forward biased, and base emitter junction is reverse biased, okay. And if you combine both the model, right, and you build it, this is like a universal model, and it is known as ever small model for BJT, where it is combination of this model and this model, okay, this model. So both are combined, and this model is used to analyze the BJT in any of the mode, either of the four modes, okay. So if it is, this is was only for active, this is for reverse active only. This is for active mode, okay. Both of them, either of them are for active mode. And if you want to analyze for any of this mode, then this is the hybrid kind of a model given by this scientist, named after the scientist Ebermol. And it is just a combination of the model that I just showed you. Okay, so this is forward and reversed, and it is used to predict the behavior of all the model of the all the modes of operation, right? Saturation, cutoff, forward active, reverse active. Okay, and if you have to write down the equations for IE is made up of this IDE. Okay, and this is this direction and this is this direction. So minus alpha R IDC. Similarly for IC and IB is nothing. What is IB? IB is given as, if you have to, what is IB here? IB is IE minus IC, right? IE minus IC is IB. Okay, so IB. So this is the same thing here. IB is equal to this minus this. Okay, so this is in this form it is written. This is just for your information. We will not be using this model. If you want to analyze for all the four modes, our analysis will be for designing an amplifier. Okay, so but on the same line. So Ebermall model gives more accurate estimate of terminal currents IB, IC using two components, forward and reverse mode current. So both of the models we have combined, and this will give this Ebermall model, which will be used. It is used to analyze the circuit in any of them. In forward active mode, when VCB is greater than 0, the leakage current in reverse bias CB junctions are very small and can be neglected, leading to original current equation. Now, what it is telling here, you know that this is reverse biased. Again, this is for an active mode, this is reverse biased. Right? Here, reverse bias was not to make this off. Here, this reverse bias is to attract the electrons and make a flow of current, create a current by attracting electrons, making electrons run. This reverse bias, the physics of this reverse bias is not to make this whole thing off. Again, understand, it's a simple logic. If you want, because these guys have come and collected, they are not moving or running. Only the current is only created if they are running or made to move. And that is done by giving a positive voltage. So if you have to give a positive voltage here, then this will be negative. So that's why it is reverse biased. And you know that if we just concentrate on this junction, which is a reverse biased one, there is a reverse current which is in the picoampere, less than nanoampere, a very small current flows. You know that, right? But that is negligible compared to this current, which is because of IE. Very small and can be neglected, leading to the original current equation, where your IC is a function of IE and not that reverse biased equation where you get hardly any current, because that current is, if that current is because of 5 electrons, let's say reverse, right, then this will be because of 105 electrons, let's say. So that reverse current is negligible or almost zero, you can say. Okay. So again, reverse bias means it is not that getting off. That reverse bias is because you have to give a positive voltage to attract the electrons to create a current. But since that junction is reverse bias, it will have a very negligible current flowing. Okay. And that can be neglected. And you can think that your current is completely because of the emitter current, collector current, or the current of this device is because of the emitter current. Fine. Okay.
Yes, ma'am.
Okay. Now we are coming, so all these four modes we have seen. This was just a starting and a brief this thing. But now you have to understand graphically what is happening. And in terms of IV curve now, okay. So here, if you see, in terms of what it is showing is this graph here. And what is this graph for? So as I said, your hero here or your current here is IC. Okay, so that's what we want, and that will make output voltage, or it will be your output current or whatever. So if there is a resistive load, this IC will produce a voltage then. Okay. So now this IC is the current that is dominating, and that's the talk of the town, that whatever you are doing, if you want high gain, IC high gain means high voltage at the output. So that output load is fixed. So your IC is more. If your IC is more, then you will get a high voltage or high gain. So high gain means you need to have high IC. So everything comes down to IC only. You have to quantify IC. Okay. And now that IC is a function of two things now. IC is a function of, we have seen that as far as your collector base junction is reverse biased, it will not make much difference. So that's what it is showing here. And IC is also a function of VBE, base emitter junction, that we will see how it is behaving. So because IC is almost equal to IE, and IE is exponentially related to VBE. So that also graph we will see. But for now, we have to do step by step. So this is VCB and this is IC. So if your x-axis is VCB and this is IC, then this is the kind of the graph that you get for IC. Now understand here, very important. This is 0 and this is minus 0.4. Okay. Now in your diode graph, if you see your diode equation forward bias, if I show you your diode forward bias, okay, if I take this curve, let's say, then you can say that if I say that, now this is reverse bias, from here, negative voltage all. But the diode is conducting after, let's say 0.4 volt, right? It will start conducting. Up to after 0.4 volt. You can say that now in case of silicon diode, let's say. After 0.4 volt, below 0.4 volt, it is conducting or not conducting diode? Then in nano, micro, ampere, and then milliampere, it will conduct, right? But up to 0.4 volt, it is not conducting, right?
Yes, ma'am.
And then we can say that up to 0.4 volt, it is not conducting, and then below 0.4 volt, it is not conducting. Correct or no? That negligible is not conducting. Okay, that negligible you forget. Practically, there is a negligible current which is almost null, but it is not conducting. The reverse is not conducting, or less than 0.4 is not conducting. Anybody has objection in that? You have to say at least yes or no to me.
No.
ma'am.
No, you accept this, okay? You are accepting, yes? That this diode is, we can say that it is not conducting for all less than 0 negative voltages, but it is not conducting up to 0.4 volt also. See, the current is 0. This is I is 0. Only then later on it will start after 0.4 volt. Now, keep that in mind. Okay, so now this is about the same thing, that this CB, for this CB junction, okay, unless and until it is greater than, now see this CB, so when you say reverse biased in NPN, see this NPN, when you say reverse biased, okay, NPN, this is reverse biased. Okay, so this is P, positive terminal, and this is negative terminal. When you compare this two, right? This is positive compared to this, isn't it?
Yes, ma'am.
पॉजिटिव है ना
Yes, ma'am. Yes, ma'am.
compared to this. Huh? So now let me go back to that graph. So understand this properly. Very important. So with that thing in mind and what I showed you, right? So your C collector, the CB, we say this voltage as CB voltage. Okay. So for as long as it is reverse biased or not conducting. Now it is reverse biased or it is not, it is as long as it is reverse biased or not conducting, right? This is in active mode. That was the condition now. See, as long as this is reverse biased. Reverse biased hoto ne? See, this is reverse biased. So as long as this is reverse biased or is not conducting. So even up to our reverse bias is less than 0, all negative. Okay. But also not conducting up to 0.4 volt also it is not conducting only. And if this is if this grade this difference gets greater than 0.4 volt or 0.5 volt, this will be in forward bias. See, this is reverse bias you took. Okay. But if this is forward bias, then these both are forward biased. Then it is not an active mode. It is in saturation. This mode. So both are forward bias. Then it is saturation. So this is very crucial. Means that this should not forward bias this junction. So it should be reverse biased and also it is not reverse bias means not conducting and also for 0.4 volt, 0.3 volt, 0.2 volt it is not conducting. Okay, so as long as this is minus 0.1, minus 0.2, minus 1, if this is breakdown, let's say at 5 volt, let's say is the breakdown, we don't want to destroy that. Minus 1, minus 2, this is fine. But this is still fine if it is 0.1, 0.2, 0.3, because this junction is still not conducting. It is still reverse biased or not conducting up to 0.4 volt. If it gets greater than 0.4 volt, then what this is conducting, this junction, it gets forward biased. Okay, it will get forward biased if you are talking of this junction only. This junction, I want to keep it. So for this junction, I have to ensure that it is less than, yes, of course, but it is not conducting up to here. Once it crosses this 0.4, it will start conducting. So for all, not only this, for all of this, it is not conducting. For all of this, it is not conducting, and hence it will keep it in active mode. For all, after this, it is conducting. This junction is also conducting, and it will make it in saturation mode. So up to 0.4 volt, that is what is shown here. Okay. So up to all of this, it is not conducting. And till that, from here, it is all active mode. And for this CB junction less than 0.4, it is in saturation because both the junctions are forward biased now. When you take this as greater than 0.4, this all of this both are forward biased and it will make it into saturation from this point. So this is 0.4, not from 0, as I just explained to you. So CB greater than 0.4 volt, the BJT is in active mode. That is this. The junction is not conducting and it is like a vacuum cleaner and it will suck it. And IC is alpha times current source value that you know. Alpha, this is forward active. When I say this now, this is for the forward active. Only we are talking now. We don't want to connect, in the nonsense way and create a problem. And as CB becomes forward bias, VCB falls below. So then if it falls, if CB becomes forward bias, VCB falls below 0.4 volt, it reaches saturation. So do you understand now what is this we are doing? That it will get into saturation. So that is this. I just explained you. Right? So it is not conducting for all up to 0.4 volt of this. See, this is positive. This has to be higher. So see, if this two difference has to be less than 0.4. VC minus VB has to be less than 0.4. If VC minus VB gets greater than 0.4, it will start conducting this junction. And it will be forward biased, but we have to keep it reverse bias or not conducting. Same thing. Both. Reverse bias is not conducting. Not conducting is you can just extend your reverse bias to 0.4 instead of 0 volt. From 0 volt. That's all. But in terms of voltages, it is simple. You are giving a voltage, unlike charges attract, so positive voltage will attract the electrons. It is that the logic is reverse bias is not for any other reason. Okay, and I'll end with this slide. So, because when you draw a circuit, you need symbols, and this is the symbol of an NPN. And as you can see here, that this shows the direction of the current. Okay, this arrow coming out of the emitter. And so this is for the NPN. The complementary of NPN is PNP. Okay, so here we will see that slide also. And this is how NPN. Okay, and this arrow is coming out. It is showing the. So if I show you here, as you can recall now, this is the direction of the current, and the direction of the current is opposite to the direction of the electrons. So electrons are moving this way, and the current is the direction of the current is this way. Okay, and in a BJT, so this is emitter, and the current is coming out of the emitter. So that's what is here in the symbol. Okay, so if this symbol is there, you must understand this is NPN, and see this is collector, base, and emitter. If it is PNP, then this is complementary. This we will have the current coming in of the emitter. I'll explain you that figure also next time from PNP. Okay, it is very simple once I teach you, but it is just complementary. For now, accept it. And if the electrons are coming out of the emitter, the current, if the current is flowing out of the electron is opposite of the current is flowing out of the emitter, the current is getting into the emitter here. Okay, and this is E. So if this symbol is given and you have to replace the model is same for both. That also I'll talk to you. The model is same, but when you make this E should be E only and C should be C, you cannot exchange E for C in a BJT. Like in diode also PN, right? So positive is positive. So yeah, MOSFET is a symmetrical device, but BJT is not. We can make it the way we want. We can fabricate symmetrical also, but we are intelligent, as I said. We will fabricate the way it gives us maximum power with minimum input. Yeah, we want more return. Yeah, but if it is money also or effort also. Similarly here also, with little input, we should get more current. So that is the goal of any electronics. And that's why this is the way we make it, right? That okay, a kitchen thoda kam chalega, but living room has to be spacious. Now you cannot go and make a kitchen a living room, right? That is not an efficient way, although you can. Okay, so is that clear to everybody? Any queries? Just unmute your mic and ask me. If you ask me queries also, you can leave your ID. That is appreciable. Am I audible or I got disconnected?
You are audible, ma'am.
Okay. I hope that was making sense to you.
Yes, ma'am.
Okay. So then I leave you with, I leave a message by today only, as we have decided. Okay, that will be, but officially I leave after some time. Okay, so have a nice day. I
Bye
will
bye.
thank you if you have no queries then.